Hello everyone, my name is Raphael Monstein, this is my colleague.
I'm Benoit Figuet.
And we will be talking about predicting go-rounds using machine learning and open source data. We will start with an introduction into the topic, and then we will talk about predicting go-rounds in the next hour. And then we have a second model which we'd like to discuss with you, is predicting go-round occurrences during the approach. And we will conclude with a conclusion. Now, first off, why is it interesting to predict a go-round? A go-round is a missed approach or a landing that has to be discontinued, usually because of safety concerns. And go-rounds increase the workload for air traffic controllers and for pilots. They can also cause additional delays and can decrease the airport throughput. So being able to predict go-rounds can potentially increase the understanding of the system of the airport that we're looking at. And it can also increase the situational awareness if, for example, the air traffic controller is presented with this information. And it can potentially increase the throughput of an airport. The system that we're looking at is runway 14 on Figuet International Airport. You see that here as the red trajectories. And one of the issues with go-rounds on this runway is that they interact with departures that can happen simultaneously on runway 16, which is what you see in blue and in green. And to do the prediction, we used data from OpenSky network, basically from the whole year 2017, 18, 19, and the first half of 2020. First, we removed some outliers and smoothed some of the data, and then we added labels. These labels contain landings, takeoffs, go-rounds, and they were done with a simple rule-based approach. And all in all, at the end, we ended up with about 250,000 landings on runway 14. And let's have a look how we did the detection of a go-round. It's also a rule-based classification. We defined an approach corridor for runway 14 and detected when an aircraft enters it. Next, we detected when the aircraft leaves the corridor, and that is usually when the aircraft actually lands on the airport. But if the aircraft stays within our system or is still observed for more than 6 minutes and it's above 800 meters above ground level, we assume it to be a go-around. With this method, we detected over 800 go-arounds on runway 14, but the method also detected some stuff that we didn't quite anticipate. For example, here you see a calibration flight for the instrument landing system, and these we don't want to include in our prediction. Also, we see flights like this, where it's not exactly a go-around, but it's more like the air traffic controller told the pilot to fly in orbit, probably to get more distance from the leading aircraft or because there might have been something on the runway. So after visual inspection of all the go-rounds, we ended up with 715 go-rounds that we are sure are actually go-rounds and that we want to include in our model. With this pre-processing done, we can start modeling the go-rounds. The first model used a number of predictors, and one of the predictors was the probability of a given aircraft type, for example the A320, of having a go-round. If we look at the A320, we observed that in the historical data we have about 2.3 go-rounds per 1,000 landings. We grouped these probabilities of having a go-round into 3 groups and used them as predictors. Additionally, we have a predictor that shows if the aircraft is a domestic airline or not. We have predictors based on the weather, and we have some predictors based on the traffic. Now, the model that we want to use is a generalized additive model. Generalized additive models are an extension of linear models, and the specific case that we want to use now uses a Bernoulli distribution to model the response variable y. what we model is basically the probability of an event given the predictors that we have. And as you can see on the bottom, this is a structure that the model could have. And the nice thing with generalized additive models is that we can have both linear predictors and non-linear predictors in an additive model. As you can see, the beta 0, 1, and 2 are linear predictors, and the functions f3 and f4 are smooth non-linear functions. We fitted this model with the 8 predictors, and you can see on the bottom you see the formula. So we have the probability being dependent on if there was a thunderstorm observed in the vicinity. We have it dependent on the type code, and if it is in the kind of risky group, or in this case the unknown group. We see that there's a dependency on how many domestic aircraft were landing, and we see a dependency on the weather. Specifically, it is depending on the visibility, the crosswind component, and the headwind component. After fitting the generalized additive model, particularly for the linear part, we can actually look at the coefficients that were fitted, and we see that we get a coefficient for beta 1, which is the coefficient for if a thunderstorm was present. We see that we get a value of 0.95. If we take that to the power of e, that gives us a factor of 2.6. What that means is the probability of having a go-around is 2.6 times higher if a thunderstorm is in the vicinity compared if there is no thunderstorm in the vicinity. And of course that applies to the other coefficients as well. Also, what's very interesting with generalized additive model is that we can model nonlinear effects. And here are the fitted smooth functions for the nonlinear part. And if we take the plot on the bottom right, you can see that there is a clearly nonlinear relationship between headwind and go-round probability. What you can see that up to a slightly negative headwind, meaning tailwind, the probability actually decreases of having go-around and then sharply increases after about 5 knots. So if you have more than 5 knots of tailwind, your probability of having a go-around increases sharply. We can also see in the visibility, which is the upper right plot, that there seems to be some kind of level, and say for a visibility between 5,000 and 8,000 meters, it doesn't make much of a difference. They seem to have about the same rate of go-arounds. But what is also clear is that the lower the visibility, the higher the rate of go-arounds, but in a non-linear fashion. If we look at the predicted probabilities as shown on this graph, where on the x-axis you have the predicted probability and the density function of the probabilities, we can see with the two colors the two groups. So the blue colors are the probabilities that were predicted for the flights that were not go-around, so for the landings. And the red curve shows the predicted probabilities for the go-arounds. Unfortunately, as you can see on this graph, the two groups do not separate very well. There's a big overlap of the two groups, which means that predicting or kind of differentiating between a go-around and a non-go-around is really hard for the model, and it only works for part of the flights. This is to some extent to be expected because the predictors that we have are relatively weak and do not achieve this separation of the two groups. But as Benoit will show in the next couple of slides, that can be much better done or if you predict it not for the next hour, but if you predict it per landing trajectory.
So now I will talk about the second model we have worked on, which is trying to predict the go-around occurrence for an approaching aircraft. So I will start to talk about the feature engineering we have done, the imbalance problem, and finally the results we have obtained with this model. So the goal is to predict if an approaching airplane will perform a go-around or not. But to do that, we'd like to use no no data from the airplane which is closer than 10 kilometers from the runway 14 threshold. The reason is because it has much more value if you can predict a go around much before it happens. So just for later on, you can see that we have an approach corridor, and you can see the 10 kilometers cutoff distance on the plot, as well as what is a glide slope and what is a deviation from the localizer on the left plot. So we have depicted three types of different features. We have the features which are associated with the stability of a trajectory. And to do that, we have extracted the glide slope angle of an approaching airplane, the deviation from the localizer, and what we call the specific energy. Then we have extracted some other type of features, which we call intrail relationship features. And this is basically, okay, how much distance do I have between a trailing airplane and the leader airplane, as well as, okay, what wake category is the leader flying, or what wake category am I flying? Then we have added some environmental and aircraft features, and this is the same features as what Raphael presented before, such as the weather, the aircraft go-around category, or is it a domestic flight or not. So let's have a look at the stability metrics for some go-arounds and for some non-go-arounds. So on this plot, on the first row, you can see the different time evolution of some stability features, such as the glide slope, the localizer deviation, or the specific energy. What you can see is that for go-arounds in red, it seems to be, those values seems to be higher than the normal landings in blue. But now, if you look at the distribution of the mean values, which is the second row of this plot, you can see that, okay, it's more spread for go-arounds, but there is still a big overlap between the two distributions. So they seem to be rather good predictors. You can extract some information from those predictors, but they are not perfect. So that's why we decided as well to include intra-relationship predictors. So to do that, we could compute, okay, what's the distance between two airplanes? So when I look at the airplane which is approaching, what's the distance with the leading aircraft? I can also look at the speed difference between the approaching and the leading aircraft. And based on those two predictors, we can compute what we call the time to leader. And then based on this time to leader, we can look at different values here on the right table. And so if I look at one approach, I can look at, okay, what was the minimum time to the leader? And we can see that the smaller this minimum time is, and the higher of having a probability of a go-around is. So this seems to be rather a good predictor. Then we have used some different features, and those are exactly the same one as what Raphael presented before, so I won't go through it, but basically we have the airplane type code go-around category. Is it a domestic flight or not? And what are the weather conditions based on the visibility, either a thunderstorm, either headwind or tailwind, and what's the crosswind? So this table kind of is describing all the features we have used for this machine learning model. So I won't go through, but this is basically all the features we have just talked about. So before we go to the model, there is something to talk about. One of the main issues we have is that we have about 3 go-arounds per 1,000 landings. So if I'm using the full set of landings as well as the full set of go-arounds to train a machine learning model, most likely it will fail. I mean, it's very easy to have 99.7% of accuracy, but this is not what we're looking for. So what we did to deal with this problem is that we use a classic downsampling technique. So what does it mean? It means you have to undersample the majority classes. So to do that, we just took, instead of taking the 250,000 landings we have seen, we just take a sample of 1,000 of them. And then we take all the go-arounds that we have. So we have 695 go-arounds. So you can see now that this is much more balanced, and we have almost as much go-around as much as normal landings. And this will help us a lot to predict the probabilities of having a go-around for an approaching airplane or not. So just for you to see something, we have done a principal component analysis. This is the result in 3 dimensions of this subset of landings and the full set of go-around. And you can see that, okay, some go-arounds can clearly be separated from the non-go-arounds, but they are still a bit of an overlap in the middle cluster, and this is not going to be an easy task. So now let's talk about the different model we have used. So we have just used very classical machine learning. So we have tried a bunch of classifiers, so linear supervector machine, round-based function supervector machine. We have tried random forests, ADA boosts, naive bias, quadratic discriminant analysis, as well as gradient boosting classifier. So just to train those models, we have used only 50% of those data, and the rest of the 50% are used as testing data. So on this slide, you can see on the right plot, the different results we have obtained for the different models. So this right plot is called a receiver operating characteristic, and is basically plotting the true positive rate versus the false positive rate. So the best model we have is the model which is closer to the top left corner. And what we can see, the random forest seems to perform better for this task. So how to read this? Okay, let's just take this example here, which is shown in this confusion matrix. And this is for a true positive rate of 0.5. So it means that this model has been able to identify half of the goaround, so 344 of the goarounds, for a false positive rate of 0.07. So it means the false positive rate is below 7%. But you can see that still over 250,000 landings, almost 20,000 of them were wrongly classified as goaround. So that's an issue that you have to consider or not. You can classify half of the goarounds, but then you have to pay the price of having 20,000 real landings, which are also classified as goarounds. Now, if you look at another true positive rate, so if you really want to get more goarounds, so we are capable of detecting 483 goarounds. The issue is then that you have 55,000 landings, which are wrongly classified as goaround. So this is really depending on, do I want to detect all the goarounds, or am I fine if I can only detect half of the goaround, but you always have to pay the price of detecting what we call false positive. So let's first focus on the true positive and false negatives. This model, as we have seen, is good at detecting maybe half of the goarounds, but now let's look at where are initiated the goarounds that we can correctly identify. And you can see here, it's on the yellow part of the plot, and we're capable of kind of detecting the goarounds which are around 5,000 meters from the runway. In another hand, we have a lot of false negatives, so meaning that we thought, the model thought it was not a goaround, but it actually was a goaround, and actually a lot of them are the ones which are happening close to the runway. So this I think we could explain because we have probably a lot of goarounds which are happening because the runway is still occupied, but because we're only using data 10 kilometers away from the runway, this is not something we can predict. So that could explain why we're not capable of detecting those type of goarounds. So now if we do the opposite, if we focus on the false positive and on the true negatives, what we have done on these plots is we have plotted the stability metrics for the false positive and for, a subset of false positive and the subset of true negatives. And what you can see is that those red ones, which looks like they are unstable, are still managing to land. And this is due probably to several reasons. The first one is you can see we have a lot of kind of kinks in the data, and this is due to noise in the data. And when you have noise in the data, you might then overshoot your mean value for the glide slope or something like this. And then, of course, you will have kind of bad predictions. Another thing is you have a lot of pilot, which we are still far, 10 kilometers from the runway, which will still manage to stabilize the airplane before kind of the window for landing. So this is one of the reasons. Actually, it's very interesting to look on the distributions of the mean values because they are really well separated between the normal landings and the unstable landings, if I can say. So, in conclusion, you have to kind of find the right trade-off between sensitivity and specificity. Do I want to detect all the goarounds, Or am I fine if I can only detect fewer go-arounds, but then I'm more confident that I won't have a lot of false positive? What is also very tricky is that the data set is so unbalanced that the model that you are developing need to be recalibrated in a way. So that's an issue of this model. And some of the go-arounds are very difficult to model because we don't know the causation. Maybe ATC is just asking an airplane to go around for a reason that we cannot model in this approach. Or, as we said before, maybe the runway is occupied, but because we don't see 10 kilometers away from the runway, then we can't model this in our approach. Something else that we've seen is that some landings manage to land despite unstable approaches. And as well, the last thing we saw is we have noise in the data, and this noise in the data might give you some wrong prediction as well. So that's it for my part. Now let's talk a little bit about the conclusion of this work.
As we've seen in the last couple of slides, we used a couple of different approaches and levels to model go-arounds. Even though the results are not always conclusive, these predictions help also to understand the system and gain insight into what are the causes and what drives go-arounds. And if the quality of the results can be improved, we think there is an operational value to use these methods and build tools out of it that can be used in the daily operation. Now, if you have any questions, we will be happy to answer them. Thank you.
Thank you.